Come on, 14, start.
Can you hear us, Ferdy?
Hey Joe, do you know what this is about?
Supposedly we're gonna have a tutorial on Arduino. We had one yesterday, and today we were gonna talk about Arduinos and motors and how to connect them and use them, and servos and yeah.
Oh, okay. Are you with John now? Sorry.
Tiny scissors, yeah.
Yes?
Tiny scissors.
There's some scissors in the toolboxes. I think it's the third one from the top on the right side.
So that board is done and evacuated. I haven't taken off the tabs and the
Yeah.
screws. Is it okay if I?
Yeah, just leave it for a while. Okay, all the Arduinos are blinking? Ah, okay.
Man ganz alles kannst du mal nutzen, muss man ein Programm auskalten.
Gut, werde ich mir anschauen. Okay, and then I would want you to go to open the Arduino and go to the examples, and there's one that is called analog input. So it's file, examples, or maybe I should share my screen. Okay, I hope everybody in Valdauda can hear me as well. And so we're starting by opening the example, which is an examples analog input. that is very similar to what we did yesterday. We measure an analog input, we measure a voltage, and then we make an LED blink. So we use the blink steps again. This time a combination of the two. So we look at the value from the sensor, in this case our potentiometer, and we change the delay in the blink so that it blinks longer or shorter depending on the value that we have for the potentiometer. And then I would want you to build something like this on your breadboard. Make it a bit bigger. Doesn't want. Now it does. So we put the potentiometer and we put one side to 5 volts and the other side to ground. You can use those, you know that those outer rails, they're all connected in rows like this. So if you connect ground and VCC on those two, you can always access ground and 5 volts on this row. And then you would go, of course you could go directly with those two to over here, but this is your choice. And difficult, like to make it a lot larger, it doesn't fit on the screen. Sorry? And this piece here, this should be in your kit, and it's a little blue component that has a little knob that you can turn. What's a variable resistor? Looks like this. Yeah? And it doesn't matter which way around. If you put it the wrong way around, it's just going to invert the values. And so, yeah, we have some of those very tiny, and then we have others that look like this. No, maybe you can try something working. Yeah, that should be good. Yeah, as I told you, if you put it the wrong way around, all it's going to do is going to invert the value.
Party.
Yeah, John.
Should we connect a resistor to the light, or is the potentiometer acting as a resistance?
Oh yeah, actually, as you can see, the LED doesn't have a resistor, and this is because port number 13 has an integrated resistor. So we can, for port 13, we can. That's the only port where we can connect an LED without a resistor.
Ah, okay, thank you.
So for this one, it's an exception.
Thank you.
Of course, you have to make sure that you put it the right way around. So remember, the long leg is the positive one, and the one that has the flat side, or the one that has the bigger thing inside, is the negative one. And so you want the positive to go to your pin 13 and the negative to go to ground. What's missing?
Just using for the
For fetch table?
the longest they have. Yes, but it's not complete. It's my own kit, but it's easy to recognize it, which is your statement.
The code, you put the codes together.
It's 5 examples, analog, and Arduino. Or just a recommendation in general, if you want to make sure that you don't burn your Arduino, you unplug it while you're putting all the cables, and once you finish, you plug it. First of all, those are Yes, do you want to already upload your sketch? Let me know when you finish with the cables so I can put the code. What's missing?
Not a USB cable for Arduino.
That's here. I can get one from the.
If you want,
Yeah.
sure, it's okay, but just for 2 hours. So blue, yeah.
Therefore, like the Arduino code is a bit different, so you could either decide to change the Arduino code so that it goes to A0, or you just put this one into A0. No, check it. But actually, I just do it like this, so we're all doing the same. I should be able to rotate the mouse and change the frequency.
Yes.
I didn't change something because I don't know. You are what
Okay, so let's look at the code and try to understand what's actually happening here. So we define, in the beginning we define some pins. You don't really have to do this, but it makes your life a bit easier. You could just, each time it says LED pin, we could just put the value 13 in here. So if you replace LED pin here by the number 13, the sketch would work in the same way. But usually it's easier to define them in the very beginning. So this is outside of setup and loop. So if you write something completely outside of this, they are so-called global variables, because you can access them in all other parts of the program. If you declare a variable in the loop, setup won't know about this. So the variables have different scopes, and who made a board right in the middle of this? Come on, like this huge board. There's lots of space in all directions. You put the 0, put it on the corner. And yeah, we took this big one so we can mill something big, and now you could have taken any of the leftovers we have. So we have like a whole bunch of leftovers all in here. Any one of those would have been big enough for this one. I don't know who it was, I don't really care. But this one would have been almost the right size.
The last question.
Okay. So we define those global variables right in the beginning. Then let's see, I think in the preferences. Better? So we define the pin for the sensor. This is where we have the potentiometer attached, the one that is measuring the voltage in A0. Then we define the LED pin, which is our output on pin 13. And we define a value just for the sake of it that we call sensor value. This is where we're going to store the reading from the sensor. Then in the setup, all we have to do is to define the LED pin as an output. You don't have to define the input as an input because it's an analog input. And in this case, we don't need to define anything because they can only be inputs. The analog ports can't be outputs. And then in the loop, we read the value from the sensor pin just by saying analog read sensor pin. And we store this value in sensor value. Then in the next step, we turn the LED on. So we write a high to the LED pin. And then we wait for the amount defined in sensor value. And if you double click on analog read and you go to find in reference, we will get to the page that explains us how this works. And since we have a 10-bit analog to digital converter, you get values between 0 and 1032. So the maximum delay that we can put is 1023. So this is more or less a second. So if you put the knob to one extreme, it's going to take about a second for it to go on and off. And if you put it to the smallest value, it should go on and off very fast. So we have two delays. One is the delay for it being on, and the other one is the delay for it being off. So if you wanted, you could, for example, try what happens if you multiply the sensor value by 5, which should, oh, something wrong on my screen. This should give you 5 seconds in the longest value, and it should give you still 0 in the smallest one, because 0 multiplied by 5 is still 0. So in one extreme, the LED is on all the time, and on the other extreme, it blinks, it's 5 seconds on, 5 seconds off. And of course, you would have to multiply this one here by 5 as well. If you just multiply 1, it will only change for the on time, and the off time will stay the same. So yeah, maybe try what happens if you multiply the two values by 5. You should get an LED that blinks much slower on the path. Oh, yeah, of course. Maybe an easier way of doing this is to go and change. Something's weird. I have to like one offset. We could also say sensor value is analog read multiplied by 5. You can also put the multiply here. Okay, this doesn't work. I think I might have to put my font back to normal size because it's not writing in the right spot. Maybe if I like this. No. Damn it. Okay, but you know what I mean. No. No. Ah. I can't work like this. But it's always one offset. See, it just skips 2 characters. Okay, so the next thing I want to do so the value between 0 and 5 volts, you need to measure this. So so value between 0 and 1. So 0 is what you command back. So 0 multiplied by 5 is 0. What about multiplied by 5? It's 1024. Our multiplied by 5 is 5000. It's 24.5 seconds. But you haven't uploaded Here's the board. Okay, the next component I want to use is this little one. It's black. It has a little label on top, and that's the for the buzzer. Yeah. Okay. So I want you to open the sketch that is under File, Examples, Digital Tone Melody. I guess it's your opportunity right now to look to the font and see File, Examples, Digital Tone Melody. Yeah? Right now is the moment. Okay? Got it? So we see that it talks about an 8 ohm speaker on digital pin 8. And so all we have to change is to go to our fritzing. Oh, you go to your breadboard. No, wait. And we take away the LED. And we put our little buzzer if I find it. And you either change the number, yeah, let's put this one to 8, so it's going to be easy. Is it 8? That's weird.
Yeah.
Okay, once it's starting to make sound, maybe leave it. make an empty.
No, because it's open and closed. Yeah. Never is low, it's not. Oh yeah, it's going to make it.
Okay, unfortunately, the buffer that we have is not really able to play different frequencies, it just goes take this one, this is playing more stuff now. And it only plays it once, and if you want to play it again, like if you look at the code, then we see that that all of this is defined as a global variable, and then all the rest is going into void setup, and void loop is empty. So the stuff that is repeating is completely empty. It only plays once, each time each other will repeat. And one way of restarting Arduino is pushing the reset button. And one interesting thing is if you no, it's working. Do you have enough?
Whose button is this?
So if you have a pizza speaker like the
Oscar Masters, trying to sheep the sheep.
Okay, this is working for everybody?
Can you go with the command?
Yeah, this is work. It seems nothing.
Okay. Okay, let's hack this sketch a little bit. Right now it's just saying it's stupid melody. One thing that I want you to note about this sketch is that it says include pitches.h. And if you look, there's another tab where there's more code in there. And so this code is defining the different pitches of the different notes. So we know that a C1 is 33 Hertz. And so we define this in here. In the end, this is just a whole bunch of variables that we define. And since they get included outside the setup and the loop, they're valid in all of the sketch. And this is a way you can like organize the sketches a little bit, that you don't have all of the stuff written in one sketch, but you can just make a new file by clicking here on New Tab. You give it a name, and then you can just say here, include pitches.h, and it is as if you had written all of this just in the beginning of your sketch. And then it says notes in melody, so it defines an array. And for the moment, we don't really have to worry about what an array is, but basically an array is a list of values. So it's a list. And so right now, for defining an array, we write something like this. Those edgy brackets are the ones that indicate that we're talking about an array. And then this is all the things you put into the array. So it's node C4, and writing node C4 is just as much as writing, well, if I find the C4 in here, no, not F, C4. So C4 is just as good as writing 262, which is the frequency of the C4 node. So if you wanted, you could start to change your melody a little bit and just try, maybe just try changing a 3 to a 2, or maybe a 3 to a 4, and listen how the melody changes. Huh? Yeah? No, pitches is an include file. It's this file that is open in the second tab. You just click here and you say new tab, and you give it a name, and then that's it. Yeah. Okay, does this work?
Because if I could fix that with my code in the other one, and it works.
Yeah. Yeah, I will go through and explain all the little things. Okay, so once you made this change, you can have a look at the node durations, and here you can change how long those nodes are on. So if you put bigger values, they will go beep, 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 beep. So play around with those values. Those define the length of the node. Okay, everybody happy with this so far? Okay, can you have another look? Should we continue or like? Yeah? Okay, so if you look at the code, we see that in setup it goes, it defines a loop, and a loop is something that gets executed several times. And we can define how many times it gets executed. And loops is something that you're going to use a lot. There's different types of loops. For the moment, it's enough to know that there's a for loop and a while loop. And the for loop, we tell it at which number to start, how many steps to jump for each one, and then up to which value it goes. So in this case, it says int this node is 0. So in the beginning, you can just start with a value that is of your choice, and you can give it any name you want. But it should be an integer in this case. So we say int this node is 0. So we start from 0, and then we go until the node is not smaller than 8 anymore. So once it gets to the number 8, it's not smaller than 8 anymore, so it would stop. And this one here, where it says this node plus plus, is just as good as writing this node equals this node plus 1. It's just a short way of writing it. And this is some of the things that are kind of weird in the beginning because this node plus, what does this mean? But it's just the same as writing this node equals this node plus 1. So you, for each time it runs, you increment by 1. Yeah?
You say it's better like to declare the variables in, for example, if you declare this node variable inside parentheses, what would
in the very beginning?
yes, in the beginning.
Yeah. This loop is only running inside our setup, so we don't need it anywhere outside. And if we were to use it anywhere outside, it would get the same value. So it would, like, we had 2 loops using the same names, we would confuse them. So in this case, we have to leave it inside the setup, and we have to put it into these parentheses. So if you want to know about the for loop, you can look it up in the reference, and it tells us that this is the syntax. So you have for an opening parenthesis, then you define some variable that gives you the starting value, and then a value that defines up to where it goes and how it increments. And inside the loop, so inside the opening curly bracket and the closing bracket, when you use the variable x, it will have the value of something between 0 and 100. So the first time it runs, it has 0. Second time, it has 1. And it would run until it reaches 100. Or actually, yeah. And once it's at 100, it would stop because 100 is not smaller than 100 anymore. And here, this one, you can have several conditions. You could also say, keep running until you're bigger than 100. But then it would always continue running because there's or actually, it wouldn't run in the first place because 0 is not bigger than 100, so it would stop after the first one. So you have to put some kind of statement that makes sense. But for the easy case, you can just look at something like this. And this is very similar to the way you would use it most of the times. So you go from 0 to a value, and you increment by 1. And I would say 80% of the times you want something like this. But let's say you want to generate something more complicated, let's say a calendar that goes to 31, and then it goes to 30, and then it goes to 31 again. Or let's say you want to define a norm of screws that come in the sizes 3, 5, 7, and 9. So you would have to use different statements and different increments for fitting those numbers. Okay, so we're running through this loop, and each time we call this function that is called tone. This is a predefined function. And the function accepts 3 parameters. One of them is the port, where it should output the tone. The next one is an array of nodes, which is the melody array. And this node, in the first case, is 0, so it would take the first node, which is C4. And it would take the node duration that comes from here. And it would make the first node. The second time it runs, this node would be incremented to 1. So it would run once again, but this time take the second node from the array.
This node, I don't see where it's defined.
The node G3 is defined here in pitches.
No, how does it in the tone function?
Yeah.
How does this node in that function relate to the integers on top?
So melody. Well, it's actually I'm going one step too fast. So I'm jumping lots of things that. But I will just give you the general explanation, and we go into more detail later. But the easy explanation is melody is an array that is composed of all those things. The first thing in the array has the number 0. So if I want to access the value that is number 0, I could write melody, melody, and then I put the curly brackets, no, the edgy brackets. I find them. Oh, come on. My keyboard is somehow weird. So for accessing the first value, I would put 0 here. Oh no. And
just define the integer, one integer, for example.
yeah, it's like here. It's like saying int my int equals 1.
Okay, so the coordinates brackets count because it's an array.
Yeah.
And then we have to.
Okay, so we step through this array, and each time we play a tone with this value. And maybe let's make this a bit easier and combine it with the last example we had. So this is the moment where you have to look outside. So I'm going to open the other example.
Is possible make
And write anymore. But you have the same example on your computer, and I will make sure that you find the right spots. So if you go and we had the analog input. So this is one sketch, and I put it on one side of my screen, and this is the other one, and I put it on the other side of my screen. So they have the two next to each other. And so now I want to take the parts from this sketch that read the analog value and copy them over to the other sketch. So first of all, we need the sensor pin. So I go in the line where it says int sensor pin equals A0, and I copy it. And I go to the very beginning of our sketch, just after where it says include pitches, and I paste it there. Make a blank space after it. And then the other value we need is the sensor value. So I go to the analog input sketch, and I copy the part where it says int sensor value equals 0. I copy it, and I paste it in the other sketch. So now our sketch with the tone melody should read include pitches.h, and then it should say int sensor pin equals A0 and int sensor value equals 0. Yeah? You got this? Everybody? Hands up who doesn't have it yet.
from only the last, only the sensor value.
The sensor pin and sensor value. The first one and the third one. No. No. Yeah? Okay, so once you have this, we go to the line where it says sensor value equals analog read sensor pin. I can put the ×5 away. So it's the first line in the loop of the analog input sketch. So we take this one, we copy it, and we put it into the loop of our other sketch. And in the loop it says no need to repeat the melody, and this is we can just override this with the value we have. I don't see any reason for anything beeping right now, like we should be coding right now. Okay, so you got this? Yeah? Let's see people clicking around, so maybe I wait another moment. Okay? And once we have this, we delete everything in setup. Oh no, wait, we copy one line where it starts with tone and says something. We just copy the whole line and paste it under the line in the loop. In my case, it says tone 8, melody, this note, note duration. And we just copy this one down from the setup into our loop. And we delete all the stuff in setup, including the last parentheses. Yeah. Everything in setup.
Is that 8 or pin 8?
8 is a pin 8, yeah. Everything that's in there. In the end, it should just look like this. And we can also delete the part with the note durations and melody.
So the delete is no when we have the tone pattern. Include that in sort of the time. So include that now.
Yeah, it's not perfect. We're not doing it. Just follow my steps and we'll get there. Yeah? And so once we deleted all this stuff, our sketch should be very simple. It just, actually we can even get rid of the include pitches and all of the things. So right now it only says sensor pin A0, sensor value 0. In setup it doesn't say anything. And in loop it says sensor value equals analog read sensor pin. Then it says tone 8. And then replace the melody by our sensor value. And note duration, we just give it some random number. Let's make it 10. Okay, what do you think is going to happen now? Pitch.
That number according to
Yeah.
that. If you change the pitch based on, I don't remember what the sensor is reading, but it's going to change.
Yeah, one sound says more than 1,000 words. So now you can change the pitch of the tone just by rotating the potentiometer. And if you want it to go like beep, 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 beep instead of beep, you could put a little delay here. If you put delay 1000 after this, it should make a beep, 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 beep sound. Okay? Noise!
There's one thing I noticed is that when I turn, like the camera doesn't make the same thing the same place. That's what
I think that is very close to the Okay, so the next component I want to use is this one. It's called an LDR, or a light sensor. It's called a light dependent resistor, or I don't know why it's called LDR, but it looks like this. Sorry? Yeah. Is yours? Did you find this one? Did you find this one? Maybe do the exercise first. Let's change the node length to the potentiometer. Keep the same pitch. But we make the type of the node different by changing the potentiometer. Then we put a delay, and the length of the delay is the sensor value. It can go from yes. And if you want the node length and the pause length to change, you will have to put here where it says 10, you could put the sensor value as well. So right now our node length is 10. Try putting sensor value in there as well. So the pitch will get higher and the node will get longer. So you get like very deep short sounds, like doot, 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 doot. Once you get higher, it goes like dee, dee. Sorry, I'm very good at imitating this. Just like a dancer. Explaining what it does. The one we uploaded last, there's no other way. No. Very difficult.
The 10 number you have there,
Yeah.
is the node length.
Yes. Yeah.
Yeah, so it's in milliseconds.
Ooh, I don't know. We would have to look in the tone library.
Oh, okay. Yeah.
But if you go here on tone and then find in reference,
Okay.
it should tell us frequency duration in milliseconds. Yeah. Okay, and obviously you could also, the sketch we had at the beginning with the melody, you could just copy the whole part that we deleted into the loop, so it would constantly repeat. And then you could multiply your array values with the sensor value, so you could play the melody in a higher pitch or in a lower pitch. And this is free to you to do all kinds of other experiments. Yeah. Maybe I can let you continue play with this. If somebody is getting bored, you can also find a way to download a MIDI file and make the Arduino play this one. MIDI files are like an old school way of representing notes and their pitches and the durations. And there's lots of websites where you can buy, where you can download MIDI files. Most of the telephones also play MIDI files. Yeah, so I'm going to give it a try. Then we do a little break, and then we continue with the live session.
Make sure that is coming from another key. No. So you can understand that now in this box.
Okay. Maybe just a replacement. No, not possible. Maybe you should read
Thank you, but you're here. Yeah, we have to walk in front of you. But we play. Oh. Hey, oh. What? No, not yet. The noise. Ooh.
Who are you? It's connected. So this section influence both parts.
The annoying one is not mine. Don't look at it. I'm just wondering.
Okay. Next, already set. Everything? Great. So yeah. Oh. Okay, so I think so. Okay. So we're gonna just have more inputs, and then that's it. Just start. No, just start. And then when you are ready. So you are like using the visual sensor. If you are good, then you are so far. If you are red, you are so close. So and then when you are like that false. So when I right now,
this question.
so just graphic system. It's still like I think so. No, this is your graphical card. I will try. I change Yeah. Master. Okay.
This is who is yours. Sure, exactly.
And this is the wall. Start this this direction.
Okay, so it's almost cut. So
Yeah. So
we can include MKR2.
Yeah, I think I have some of them in there already.
Okay.
Next time you do the board, don't get it over that. Very, very bad.
That's not my.
Whatever it is, don't get it over that. Yeah. There you go. Okay. Okay, another day.
We could call this thing.
Coils. Okay, who's missing the number? Yeah. Okay, now we want to modulate the pitch with the potentiometer. Let the dogs like that. Okay, ready? Yeah. So I would want you to take this component here. It's the LER, or you can also call it a photo sensor or a light sensor. doesn't have polarity, and it's actually a resistor, but it changes resistance according to light. If there's more light, it has less resistance. If there's less light in the darkness, it has more resistance. And so if you wanted to wire this one up the same way as our potentiometer, the potentiometer has this little thing going where there's one. So our variable resistor was something like this. It's a piece of ceramic that has a resistance. And so if we have 5 volts here and ground here, then depending on where we put our little pin, we get a higher or lower voltage depending on where we move it. And so you can see if it's at this position, there's like a small resistor here and a big resistor on this side. So this is the way we do it. And at this point, we measure. And if we use the LDR for the same purpose, we just replace one of those two resistors with the LDR. Which means that we still need another resistor on the other side. If not, we don't divide anything, but we just get some. It only works if we have a voltage divider. So if you either Google for Arduino LDR or look at the screen, just quickly turn my screen sharing back on. And you will find something like this. So it's just the same like the variable resistor. We put 5 volt on one side and ground on the other. And we connect the LDR so that it goes up to the middle, and then from there on it's a resistor. And in this case, they're using a 10 kilo ohm resistor. So the 10 kilo ohm resistor is brown, black, orange, and then the golden one. Brown, black, orange, have a look. If you're not sure, you can also measure it. So whenever you're in doubt about the value of the resistor, the easiest way. So for measuring a resistor, you have to put your multimeter onto the thing where it says it has its own sign. Looks like the Greek letter omega. And this one is an auto range one. On some multimeters, you have to put it to the right range. So if you know that your resistor is 10 kilo ohm, you will put it onto the 10 kilo ohm thing. And actually now, I think all of our multimeters are auto range, so we don't have to worry about the ranges. And then if you give me this one, then you just put one side on one, the other on the other, doesn't matter which is wrong. And it tells us that it's 300 ohms, so this is the wrong one. And it should be brown, black, orange. This is brown, black, orange. And it says 9.6 kilo. So this is what the golden thing means. It says that we can be 2% off of the value. So it's going to be okay. Brown, black, orange. Not brown, black, red. Should be brown. Orange. No, actually, this is the orange and the red is okay, anybody else in doubt about their resistors? Yeah. Brown, black, orange, or red.
What's the value of that?
10 kilo. You see the decay there, which means kilo ohm. It says 10 and it says kilo ohm. borrow one from your neighbor. So we put it in the for no for brown, yeah, orange. For the time being, you can leave all. Maybe you take out the potentiometer instead of this one, or just. Well, if you just have this, it's already good. Is this readable? Yeah? Yeah. Okay, so one thing that is a bit essential in this example is that the LERs are not all the same. So just by the way they come from the company, they have quite different values. So you might have to change your code a little bit or change the resistance, but for the moment we just want to make it do something. We don't really care if it's exactly the right value, but they're a bit different, so that's just something to know. Okay, is this working? Okay? So once we have this, we can open the sketch that is called File, Examples, and I think it's in Basics, Read Analog Voltage. The same one we used yesterday, but this time we read another voltage. So if you followed the fritzing, then your input is A2. So we will have to change it in the code. And if you look at the part where it says int sensor value equals analog read A0, you just put A4 or whichever one. You can choose if you change it in the code or you change it on your breadboard. But this one is reading from A0. And once you have this, you can upload the code and then open the serial monitor and it should show you some values. So this is, you have to imagine it like the variable resistor. You put 5 volt on one side, 0 volt on the other, and in this case, both resistors are changing. So if you put it more to the right, this one is getting bigger and this one is getting smaller. In our case, it's only we substituted by 2 resistors, where one of them is our LDR, but only one of them is changing. But this is already enough for measuring a variable voltage between them. So if you upload these tests, so if you okay, of course you can also try taking like your light from your camera to see if it was light. Okay, so now I want you to take the beeper, the buzzer, and make it play a tone according to the brightness of your light. So all you would have to do is go here inside the loop, and we write tone, and if you write it, it already puts it in the right color. And then I open the parentheses, and remember that the first value is the port that we want to write to. So you can choose whichever port you want. Let's say you put it to digital 5. Well, actually, I'll quickly put the setup here. So I get my buzzer. There's the buzzer here. Actually, I can just put it here. So I make use of the ground of the other one. And then I make one from here to, let's say, pin, what do we have before, pin 8. Up. I thought there was a way of bending the cables. Oops. Is this understandable? Not very much, huh? I thought there was a way of giving them. Okay, so maybe if you remember the tone library. So you got this? So we write tone, then we write the port, which is 8. Then we write the pitch that we want to have, which is our sensor value. And then no duration, let's make it 10. Then we put a little delay after. Let's make a delay of 100. Okay, can you see this now? Now the pitch changing according to your volume. So the darker, the brighter it is, the deeper the tone. And of course, now you could try what happens if you multiply a sensor value by something. Multiply it by 2 or by 0.5 and see what happens.
So the function that is basically called
yeah, it's a library making. Hey, Valdauda, can you hear our beautiful orchestra? They muted us already.
I'm deaf. I'm almost deaf. Mr. DJ.
And I think I will show the sketch again, and not the according to the things in the sketch.
Try multiplying it by value or dividing it by value. Yeah, this one is quite cool. Nothing changes.
Okay.
And try to multiply by maybe. You don't have to see more. Okay, let's do something different. So you can basically get rid of all your stuff. And we'll need an LED. I know, yeah, maybe let's get rid of everything. So now all we need is an LED connected. Just something simple like this. But we put it on port number 3, and as you see, the 3 has this little tilde sign next to it, which means that it's a PWM port. Back off everything and connect an LED. Port 3. 3. Maybe make it a bit bigger. No, in this case we want a 100 ohm resistor. No, 220. 220, yeah. And 220 is red, brown. Oh. Sorry?
Red, brown.
It might look rather like orange brown, but you can also
Red, brown.
220. 220. Thank you.
Yeah. Red, brown. Or red, orange, brown.
I think it's red, brown, but I'm not sure. You're allowed to just measure.
It is brown, black, brown.
We put red, brown.
Brown, red.
No, it's red, brown.
It's one for orange.
It's wrong, red, brown. Take it, look.
I look at everything. There are 3, so
Yeah. So 220 ohms.
So pretty orange from that is the right one. Orange, brown.
The same. Red. Okay. So now let's close.
Circulate. Remember which one's circulate.
I mean, what?
Just stick it in. Does you want this then, the resistor to any other? No. Negative. Positive is the one with the longer leg. Yes. There you don't see how long the legs are. This is your leg. The longer leg is this is positive. And then you go to the resistor from the other leg to somewhere else. It also doesn't matter if you go to the resistor first and then to the leg, or to the as long as the positive is connected to the pin, the other one to ground. It's the one that you have in your list. Brown, brown, red, red, brown. Oh, it's orange, orange, brown. So there's one to have this associated, which is actually also.
And I just, I'm not sure because it's like, you know, I'm doing my holiday. Because they don't have this.
Okay, maybe just for making sure that this all works, we go and we open the Blink sketch. So, file example basics Blink. And then you change the port from 13 to 3 and see if you let Blink. Is it Blink? Yeah. Oh, come on.
If you have another table, I will try it. I'm not going to get it.
Okay, I'm sorry, I want to show you a PWM animation, but unfortunately my machine is blocking Java. And now it's getting more and more difficult. Oh, come on. Oh, years later. Oh, come on. Oh, come on, why doesn't it just open this? Okay, so I want to explain one concept that we're going to use a lot. William had a quick word on this yesterday, the full switch modulation, or PWM. And so let's say you have a motor connected to your Arduino. So when you plug one into digital output and one into ground, and you put the digital output on high, what's going to happen? Motor's going to spin. Yeah? So let's say we want to change the speed of how fast the motor turns. What can we do? Yeah. So let's say you have a big motor that is connected to the power, and you have a switch. And if you wanted to run the motor at half its speed, you could try what happens if you turn it on for a second and then off for a second. On, off, on, off, on, off. The motor will always start turning and stop turning. Start turning, stop turning. Since it has some inertia, it will just run. Your switch longer in the on position than in the off position, it's going to run a bit faster, right? And if I only turn it on very short and then leave it off for quite a while, it runs very slow. And this is basically what PWM is like. So you have our voltage that goes from 0 to 5 volts. And And let's say I turn it on half the time and turn it off half the time. I will get like half time on, half time off. Time on, half time off. Let's say I want to rotate it a bit faster. What would I have to do? I would have to keep it on for another time. So this and the time of on compared to off is called the duty cycle. So if it's same time on, then it is off. It's called a duty cycle of 50%. If I draw a duty cycle of 80%, I would have to keep it on for 80% of the time, and then turn it off for a short while. Then I turn it on for 80%, and then I turn it off for a short while, and so on. What would a duty cycle of 30% look like? Yeah, so it's 30% on, and then off. Then 30% on, and then off. 30% on.
First, do it does not on. You say 30% is the percentage is on.
Yeah. And the frequency is always the same. So it always takes the same amount between the on and offs. This distance always stays the same. And if we have the time value for this, is a few milliseconds. So if we divide 1 by this value, we get the frequency. And usually we have frequencies that are quite high for the PWM. Let's say like 16 megahertz. So it's much faster than you can ever manage to turn a switch on and off. And yeah, that's it. So easy. Normally, the base frequency stays the same, but for different applications, you want a higher base frequency or a lower one. But while you're using it, the frequency stays the same. The only thing that changes is the time that it's on or off. Like if you have any questions, please ask now, because soon we're going to just assume that you know what this is. And we can use this for many things. For example, we can use it to control the speed of a motor. We can use it to control the brightness of an LED. We can use it to adjust how much it is, for example, heating something. So if I would take like a resistor wire and I make a coil and put my power supply, and I do the same trick with the turning on and off, I would change how much it heats. If it heats more or less. Or you could use it, for example, if you want to transform a DC voltage from a lower voltage to a higher voltage, we do the same trick that we do with the light bulbs. So we, with the neon light bulbs, so we generate a very high voltage. So we take a coil and we run current through it, and the coil produces a magnetic field, and there's energy in this magnetic field. If you turn the power off, the magnetic field is still there, and it wants to escape, and it wants to keep pushing the electrons in the same direction that we've been pushing them before, but it can't because we unplugged it. And so it generates a very high voltage peak, and this way you can generate sparks, and this way you can generate a spark that goes from one end of your light bulb to the other, of the neon light. So by disconnecting a coil very quickly from a power source, you can generate very high voltage peaks. And if you do this switching on and switching off with the PWM, you can control how high those peaks go up. So you can, for example, take a 1.2 volt battery and generate 5 volt out of them, just by using this trick where you just quickly turn on and off the current together with the coil. And so we can pump it up to, let's say, 5 volts. Or let's say you want to make an electroshocker with it, like you do electroshocks, so you can do the same with but you have to fit the coil to the PWM frequency, but then you could like do all kinds of funny things with this. And also for controlling a servo, like there's a little servo here in your kit. This one has 3 cables. One is for ground, one is for 5 volts, and the other one is for telling it the position where it should go to. how do we tell the servo position? We could send it an analog value that says if it's 5 volts, we want it all the way to the right. If it's 0 volts, we want it all the way to the left. But the Arduino doesn't have an analog output. This is something that, I don't know if Guillermo left this very clear yesterday, but Arduinos don't have an analog output. We can do something that is called analog write, but it's not a real analog output. So the analog write, what it's actually doing is PWM. The funny thing is, if you take a voltage that goes like this, and you let's say we connect, this is ground, and we put a capacitor, or actually proper sign for capacitor, these 2 plates. And here we connect the pin from the Arduino that has the PWM. And then we measure here with a multimeter, and we will see, instead of going up and down all the time, it kind of averages between those values. Because the capacitor stores a little bit of energy, and once the voltage goes down, it releases a little bit of it. So if we do this fast enough, we get something that is almost a constant voltage. Even though we're not really producing something, a real analog value, if you combine it with a capacitor, we can make it look kind of like a nice analog voltage. So we don't have a real analog output, but we can cheat by using PWM and a capacitor. Is this more or less clear? So, for example, the spindle control of the Pressix, this was what we had so much fun with, and was going nuts. It just went had random values. So there's the little green box that is right next to it. It accepts a voltage between 0 and 10 volts for adjusting the spindle speed. Same thing for the shock motor. But our computer, it's a regular computer, doesn't have an analog output. But it has digital outputs. And if you switch them on and off quickly, doing PWM, we can pass them through a capacitor, and this way simulate the voltage that we need for controlling the spindle speed. So what we did is we connected one of the outputs from the computer to a capacitor, and one of the cables to the controller of the spindle. And this way we can control the speed of the spindle. And for this little motor, we do the same thing. For telling it where to go, we send it different PWM duty cycles. So if you take a very low PWM duty cycle, it goes one side. If it goes somewhere in the middle, it goes in the middle. And if you put a high one, it goes all the way to the other side. So PWM is used a lot for controlling all kinds of things. Many times you wouldn't use it just the way we do it right now with the LED, but maybe we have a look at the LED first, and then I'll explain you how we will do this with the motor. So, yeah, and let's quickly look at this. I think
in my other videos, you might have heard me talk about PWM, or pulse width modulation. In today's video, I'm going to go into more detail on what PWM is, and how you can build a PWM circuit that can dim lights, control the speed of a motor, or change the amount of power going to pretty much anything you want. So let's start with a description of the waveforms. Here's what 10 volts DC looks like, and here's what 0 volts DC looks like. Now let's see what happens when you have 10 volts being switched on and off. Right now you can see that the waveform is 10 volts half the time and 0 volts half the time. Since it's 50-50, we say that the waveform is a 50% duty cycle. Since the 10 volts is only there half the time, what you end up with is an average voltage of 5 volts. Now let's change the duty cycle. Now the wave is only on for 10% of the time, so we say it has a 10% duty cycle. 10% of 10 volts is 1 volt, so we end up with an effective average of 1 volt. So you can see how by changing the pulse width, we change the average voltage seen by a circuit. We call this technique pulse width modulation. Now the easiest way to generate a waveform like this is with a function generator. But most people aren't going to drop $100 to get one. But that's not a problem. You can build a PWM generator circuit fairly easily, and all you need is a few parts that you can get from any Radio Shack. So here's the circuit diagram. The key component is a 555 timer chip. You can get one for about $2. When you configure the 555 in this way, it puts out a square wave that is pulse width modulated. You can change the duty cycle by rotating
the part that I wanted
to
get is like the one where you see how it changes the width. No?
The potentiometer here should ideally be 100 kiloohms, but a 50K, 10K, or even a 5K pop will still work.
Okay, so this here was the only interesting part. Yeah, so we don't need the 555 timer because we have the Arduino. And yeah, all the little chips that we use also have PWM. And like if you get more expensive chips, they have real analog outputs. And actually, it's quite complicated to make a real analog output. And things that have real analog outputs are, for example, your graphics card. Your telephone probably doesn't. Your telephone probably is cheating with PWM as well. So you get a worse sound quality. But if you change, like if you imagine that, that a normal sound wave looks somewhere like this, so like a sine wave a little bit. We could emulate this, and I just take like a small part of this. Let's say we want to, it goes up and down. We can emulate this by putting some PWM with a very high frequency. At the beginning it's a bit lower, so we do very short PWM thingies. And then we make them, oh no, sorry, like I changed the frequency, but my frequency should always be the same. So like, and then in the beginning I only go like 10% up. Then I go a bit longer, maybe even longer, and then I start getting shorter again. So by varying the proof width, and this is like maybe this whole thing takes a millisecond. But since we can do PWM at gigahertz, like it's so fast that I can't even perceive how fast it is. But this can be super fast enough for simulating your voice when you're talking on the phone. And so this is kind of cheated analog output, but this is the way your phone probably cheats. And if you want to have real analog output, you have to spend a bit more money on your microprocessor. For example, the new one, the X Megas that Neil is like now putting new into the library, they have real analog output, which is handy for some stuff because you don't have to. They're much more. They don't. Like if you do this with the capacitor, you get all kinds of weird effects that we would like to avoid. It's not as clean as we want it to be. So if you want to have nice and clean analog output, you should buy a board that already has this. Yeah, so the Raspberry Pi doesn't have it. Normal computers usually only have it in the sound card. But yeah, this is the places where you would find it.
Why do you use it?
Because if you would put this one, the milling machine wouldn't know what frequency to put. It would only see like 5 volts and 0 volts. It would just go crazy. So you have to put the capacitor for smoothing it out a little bit. The capacitor, you can imagine, like if you take the picture with a, let's say you have a water deposit. Water is running out, and it runs into a big bucket. This is our capacitor. And then it runs from the big bucket into a sink. And the sink is very measured. So if we constantly pour water into the deposit, it will flow all the way through and you have a constant stream of water in the bottom. If I fill the deposit just by putting 1 liter of water and then waiting a moment and putting another liter of water, if I would measure without the bucket in the middle, I would get a liter of water, nothing. Liter of water, nothing. Would be the PWM. But if I put a big deposit somewhere in the middle, the water would accumulate in the big bucket in the middle, and instead of coming out just liter by liter, I would get a constant stream that is kind of the average between the stuff I put in. So I would get, instead of getting 1 liter per second, I would get, and then 1 second nothing at all, I would get half a liter per second, but constantly. Does this make any sense? The water example doesn't always work, but in this case it works nicely. So it's kind of a buffer. It's like a little battery. And so whenever our duty cycle is down, it kind of fills up with the stuff that we had in our capacitor. And so let's go to the Arduino and go for a sketch that is in File, Examples, and we want the. Actually, I will take the fading, but then we will cripple it so that you see the essence of it, and then we will reassemble it. Okay, so we take the fading, file, examples, analog fading. Found it? And so we'll have to change the LED pin, which is not 9 but 3 in our case. And then we can just upload this one and see what happens. Oh, sorry, I haven't connected. Yes, okay. So the fading is working? No, this is working. Okay, so you can see that your LED is slowly getting brighter and dimmer. But the code is a bit, it's not super complicated, but we can see that there's, yeah, let's do the following. We go and copy the analog write, this line where it says analog write, LED pin, fade value. Yeah? We copy this one, and then we delete everything in the loop. And paste it again. So right now, my whole sketch is just this. Setup is empty, loop only has this value. And next we have to change, like we don't have a value for fade value, so let's just put 50 in here. This value goes from 0 to 100%, which is the duty cycle. So if we put 50, the LED, oh no, probably it goes from 0 to 255. Let's check. So value, yeah, between 0 and 255. So if we put 125, it should be half off. I think it's Alt-Enter, but you would have to double check. Yeah, it's Command R. Yeah, I think it's Alt-Enter, but I'm not. Maybe Google for it. Okay, and processing is identity. Okay?
Yes.
And what does the LED do?
It's
Very low. Yeah. So let's put a high value. Put 255 and up on it again. That should be all right. And if I'm putting low values, just for seeing, just for getting a feeling of what's happening. So it's too low.
we reach the highest value.
But now it's set pictures, maximum.
Yeah. Control U. Okay. So, yeah.
Now the alt control.
Okay, so now we see, great, you can control the brightness of an LED with this. Let's see if you can control the position of a motor with it. So let's take the little motor. Yeah? So this is a digital motor. Yes. So for finding out which tables are do what on the servo, the easiest thing is to just Ruby for it. So if you write servo brown, red, orange, it will give you some pictures where it tells you that the brown one is the ground, the red one is the VCC, and the yellow one is the signal. And you can actually take a patch table and stick it into the connector, and then go from there to the red one. And so what you want is, if you unplug the number 3 from the LED, you stick it into the yellow one of the servo, and then you go to VCC cross. Once you connect it, your servo should do like a little. So you stick the yellow one into where the LED was, to the pin 3, and you put the red one to 5 volts and the brown one to 1.
Yeah.
No, you take a double wire and you see. And just for everybody, you can just take a double wire and stick it into the connector of the servo.
Okay.
So that's enough.
Can you show the pictures?
Brown is negative, red is positive, and yellow is the signal number 3.
Something like that.
I want to show you something else. You put the page, right? Yes. But this is why I didn't want to go so far yet.
What have I done wrong about the motor pausing?
That's okay. Yeah. Okay, so if we look at a data sheet, like if your servo goes, turn it off immediately. It's the quickest way to destroy your servo. If it's just going and it flickers a little bit, that's okay, it's no problem. But one thing that I want you to see is if you look into a data sheet from a servo, it tells us that the pulse width modulation should be between 0.75 and 2.25 milliseconds. So the absolute zero doesn't happen, and the absolute max also doesn't happen.
Yes.
So we want, instead of going from 0 to 255, we want to go, let's say, from 20 to 200, or from 50 to 200. So, yeah.
It's very
Well, just goes to one position. It says here. Oh yeah, but also like the servo is close to the maximum power that your keyboard can deliver. So what might happen is that Windows recognizes that you consume too much power, and it does a ping-pong sound, which means that you unplug the USB. Because it unplugs it automatically for you, and suddenly you get some computers going ping-pong, ping-pong. And yes, so this might be the reason why you use
this is like a charging port.
Yeah. So it should have enough power.
Yeah.
But yeah, depends on the computer model a little bit. This is right at the limit. I think we're like, and normally USB ports have like 300 milliamperes at 5 volts, which is the limit of what you can do. So, case converter is just having one to ground, 25 volts, and one to yeah, it's okay. And I make it simple so you understand the concept, but of course you could constantly set different values and it would like move the assembly to whatever you want to. But I want you to see that there's a limit. So if you go to M0, it's going to go, and it's the same for 255. So I want you to find out the range of the
But now, it's still in some.
yeah, it's like the position. If you rotate, possibly you will go back to the position. No, technology. Now try and maybe you can try training sketch. So we know that 50 and 150 work. Okay, so if you go back to the sketch with the fade value, the fading, so I just hit Control Z until I get back to this part. Oh, you just reopen the fading one. And now we change the range, because if you go from 0 to 255, it's going to make annoying sounds. So in the first line, where it says fade value equals 0, I put 50. And then I put fade value smaller equal to, let's say, 150. And I do the same thing the other way around on the other line. And then try uploading this one. This one is adding 5 until it gets to 150, and then it's subtracting 5 until it gets to 100, until it gets to 50. It's 2 for loops. First one is the one that adds until it gets to a certain value, and then it goes down again. Now your motor should go like forth and back.
If you start from 0, this can actually scratch.
So that's what happened.
Yeah, so
I don't use this one, use a smaller one. Maybe if you have another one.
trying to do the
Yeah. Let's see if I have more slow.
Yes, I was working, but it's not a producer from. So,
I'll give it a try playing the delay, and so it goes faster or slower. This is only Yes, there's also a several library which makes it a bit easier, but the basic thing is the same. But now we have like preset values for the that we can use. And I should find out what this is. Okay, maybe if you want to exercise, yeah, try to connect the potentiometer so that it controls the position of the motor. So instead of sending the fade value to the motor, so basically what the code would look like is something like this. So all we need is the analog write. And we should do an analog read first of the 40 pin, which is the one that you defined, let's say A0. One leg to ground, one leg to 5 volts, and the middle one to an A something port. No. Ah, what was it? Okay, so if you want to put this code, something's going to be wrong. And if you pay attention, you should be able to identify what's wrong with this code. Hint, our analog input reads values from 0 to 1023, whereas our analog write wants values between 0 and 255. But if you try it, it's still going to do something, but it's not going to be right. But once you're there, I can show you a trick how to get those two ranges. The easy trick is divide the value by 4. Yeah, so you just put the potentiometer in, you put one leg to ground, one to 5 volts, and the middle one to the A0. And the rest you can all leave it the way it is, and then you should be able to change the rotation of the servo just by turning the potentiometer. I'll show you. So we have this one, and we have this third one.
Sorry, Ferdi.
Yeah, John?
Could you show me the code again? I was doing the circuits first.
Oh, it's like this. Can you see it?
Yeah, thank you.
It's very simple. It's just taking the value from the analog read and putting it into the analog write. But it's wrong because the analog read delivers values between 0 and 1023, and the analog write wants values between 0 and 255. So we have to use something that is called the map function. And if you just write map and then go to the reference, it should tell you that the thing works like this. So we can just copy this little piece. And so first we want the value, which is val. And then we want the input range, and then the output range. So like this, it should work.
Okay, thank you.
You either do the map, or you have to write a manager.
Well, I just, when Anton wrote me back this back, I blew last week. He said there was a full spot, I still think it was full spots. So just, yeah, I think it was spot on. Yeah, I thought it was a spot on. Just outside. It's not like it's I probably back
And then this test is going to be divided into okay. But since this value goes only do 5, so then you can do either 5 or 4. All we do is check the maximum.
Cordy?
Yes?
I have a question. I know that the servos, they normally have a 180-degree freedom of movement.
Yeah.
And we were talking about the PWM and how we can set the degrees. Can we precisely set the degree, for example, 45 degrees? Or does it change the value of the PWM depending on the servo you're using?
Oh, like if you look in the datasheet, and I think a second ago I showed a datasheet of a servo. Let me see if I can find this one. So if you look at this one, it says pulse width modulation.
Yeah.
So 0.75 is the one extreme, and 2.25 is the other.
Right.
And there's 20 millisecond intervals. So anything in between, it doesn't care.
Okay.
So this is probably 0 degree, and this is 180.
180. Right.
So you would have to do the calculation of what this would correspond to in your
Unique channel.
and this way you can figure out.
Okay, okay. Thank you.
Yeah, because we yes, because you can't move the voltage. Okay, so if you look at this here, you see how it's supposed to work. So I can move it in one direction and then the other. If I move too far, it doesn't great sound. Okay, I'm going to avoid it. But the between those should be fine. If you overdo it, it will either turn in one direction or not do it. And of course, you can buy servers that are a lot bigger, and yeah, that's the server. So there are servers that just go 180 degrees, there are others that go 360, there are servers that turn all the way around. Of course, you could also try connecting it to a light sensor, moving the server to the light sensor.
No, it's possible to do some code in
yeah.
Because I changed it. I restarted it. Sit there. Like, non lo stai parlando a noi. Have saved this page before.
Always make the more positive one in the right color. Okay, I think that's it for today. Tomorrow more. Any questions from Valdaudo or any questions from here? Okay, if not, then see you soon. Bye bye.
See ya.
Olha, tem que abordar os práticos.